Hi, I'm Dave. I'm a Clojure developer from the UK, and I'm a hobbyist programming language designer. I like Lisps, I like writing Lisps, and I like writing Lisps in Lisps. So if you like those things too, please, please, please come and see me afterwards. Today, maybe unsurprisingly, I'm going to be talking about Lisps. And in this talk about Lisp, we're going to be writing a program that uses Scheme, Python, and C interchangeably in a single file. Easy, right? Well, before we get there, we're going to take a look at the rules of Lisp evaluation and understand how a Lisp program is actually executed. Then we'll take a look at Autology, a Lisp that I've written that can modify its own rules of evaluation by rewriting its interpreter at runtime. We'll take a look at some of the weird and wonderful things that Autology can do, and finally we'll use Autology to write a program which switches between Scheme, Python, and C interchangeably in a single file. I promise we'll get there. It's good. And while we're doing this, we're going to be asking ourselves in a very general, non-rigorous way, what is a language? Is it the code that we write? Is it the syntax of that code? Is it the rules of evaluation? Or is it the interpreter itself? Or is it some kind of abstract semantic category transcending all of these concepts, which they themselves become increasingly ill-defined as we probe at the boundaries that distinguish them? Well, let's look at some code. So here is a Lisp. It's an entire language in a single function, possibly my favorite function ever. Just to be really clear, we're going to walk through it together just so everyone is definitely on the same page here. We're defining a function called evaluate. It takes two parameters, an expression e and an environment env. Now, the expression e is the code that we want to evaluate. This will either be an atom, which is like a single thing, a number, a string, a variable, or it'll be a list, which might be a collection of data, a function call, or even a whole program structured as a tree. The environment is a map, and it holds the names of all of the variables and functions currently in scope along with their values. If the expression is not a list, then we know it must be an atom. If it's a symbol, a variable name, then we look it up in the environment and return its value. Otherwise, when the expression is not a symbol, then it's just a literal value, so we can return it as is. If we are dealing with a list of expressions, we're going to do three things. First is evaluate the first element in the list, and we're going to assume that this returns a function. Then we're going to evaluate the rest of the elements in the list. And step 3 is to apply the function returned by the first element to the values returned by the rest. And that's it. You know now how to write your own Lisp. It's a whole language. Not a very powerful one, sure, but it's only 9 lines of code. This is about as simple as Lisps get. We have the ability to evaluate basic expressions, but not much else. My language, Autology, is slightly more complex. It has a couple of edge cases to the normal evaluation rules, and in Lisp we call these special forms. First of all, it has the ability to define variables with bind. We supply a list of symbol-to-value binding pairs, and then a body expression. And these bindings are lexically scoped, so they're only available within the scope of this binding expression. We also have the ability to quote an expression with quote. This means we don't want to evaluate the expression, but just return it as it is, a data structure, a list. So this is it. This is the Autology language. We can evaluate atoms. We can evaluate lists as function calls. We can bind new variables, and we can quote expressions without evaluating them. There's not much to it. So we have an interpreter. It's a function, and it takes a tree of lists representing some program that we want executed. But our interpreter is written in Lisp, so it too is a tree of lists representing a program that we want executed. This lets us do some pretty silly things. So instead of our interpreter being a defined function called evaluate, let's take the literal data, which represents the interpreter as an anonymous function, store it in an initial interpreter variable, and then stick that variable in the execution environment under the special symbol I. Now, we define a new evaluate function, which grabs the interpreter data from the environment, uses the parent language, Clojure in this case, to evaluate it into a callable function, and then uses this to do the actual evaluation of the expression. Now, what does this do? Well, nothing, actually, by itself. The language works just as it did before. But instead of our interpreter being a function, it's now stored as the data that represents a function, and it's turned into a function each time we want to evaluate an expression. However, we now have access to this special symbol I inside the program that we're writing. If we were to rebind this variable to a new tree of lists that represent a different valid interpreter function, then any code within the scope of that binding will be evaluated using that newly provided interpreter. This new interpreter completely ignores both the expression and the environment and always returns the number 42. Is this useful? No. But is it a new language? Also probably no. Maybe debatable. How can we make this better? Well, writing a whole new Lisp interpreter every time we want to modify the language is a bit of a pain. So Autology provides a couple of helpful mechanisms to make things easier. First of all, our actual Autology interpreter looks like this. And don't worry, we're not going to go through the whole thing. It's not actually meaningfully different from the minimal Lisp we already looked at. But if we look at just a small section of it, we can see that the different sub-expressions of our interpreter are tagged with these little ATL markers, keywords in Clojure. These markers label the different sections of the interpreter, and they give us an easy way to refer to different parts of it and modify different sections. And Autology provides a few utility functions that use them. We have getMarker, which for a given interpreter and marker will return the data structure of that section. And we have replaceMarker, which takes an interpreter, a marker, and a new data structure to insert in place of the original marked expression. Okay, and with this, we can actually start using the language properly. Now, Autology is actually missing a feature that many other programming languages have out of the box. Functions. There is initially, at least, no way to create a function in an Autology program. Turning up at Lambda days with a language which has no functions is a bit embarrassing. So let's fix this. We can write an Autology program which modifies its own interpreter to add functions to the language. So first, we're going to grab the eval list section of the interpreter. This section is responsible for evaluating lists, and it consists of a case statement switching on the first element of the expression being evaluated. Each special form here is a pair of a test value and a result expression, and then there's a final default expression at the end with no test value. So to add a new special form to this data structure, we need to insert a new test value and result expression before that final default expression. So we're going to do that. We'll grab the eval list section and bind it to a variable original. We then define the new special form, a quoted list containing our test value, in this case just the lambda symbol, and our result expression, which is what actually handles creating a function. Then we're going to rebind I, replacing the eval list expression with a version where we splice in our lambda special form before that default expression at the end. And now we can immediately use this new feature. So let's create a function called double. We'll bind this symbol to a function using our new lambda special form. It takes a number n and adds it to itself. Then we can invoke this new function a bunch of times and end up with a predictable answer. The fact that this fits on a single slide, I think that's really cool. We have a language here that does not have functions, and yet does have the ability to modify itself so that it does have functions. I think that's wild. I think that's cool. The other mechanism that Autology provides to make this meta-interpretation easier to work with is a special form in the interpreter itself, called withI. This special form is similar to bind in its structure, but it only binds to that special I symbol. And it allows you to bind a pre-existing interpreter so that you don't have to actually define it within your Autology program. For the most part, this is just for convenience. Pretty much anything you could do with the special form could also be done manually by rebinding the interpreter in the program. But sometimes it's a bit of a hassle, especially if you're switching back and forth between different interpreters in the same program. But why would we want to modify our language? Autology is great. It's a Lisp, it's functional, it's pure. These are great things. But sure, every now and again, it's a little bit difficult to express something in its single body expression, anti-imperative style. So, what if it wasn't pure? What if it wasn't functional? What if it wasn't a Lisp? Here's an Autology program that uses a predefined scheme interpreter. A scheme is another Lisp, and it has a really minimal specification. So writing a fully compliant interpreter for it is actually pretty straightforward. That's what we've done. Now, because of this, in quite a real sense, we are actually writing and executing genuine scheme code, which is kind of cool. But what else can we do? Here is an Autology program that uses a predefined Python interpreter. Python is an interpreted language, so this isn't too crazy, right? But this isn't actually a full implementation of Python. That'd be a lot of work. It's just enough to get the very basics, like variable assignment, arithmetic, function calls. But this highlights something quite cool. You only need to implement the aspects of a language that you actually intend to use. Presumably, the programmer, in this case, really likes the way that array products are expressed in Python with NumPy. So they implement the minimum viable interpreter, and now Autology becomes expressive and concise in the desired way. Let's go one step further. Here is an Autology program that uses a predefined C interpreter. I still can't quite believe this works, but it really does. This program actually does print hello world, and it faithfully simulates the imperative stateful for loop with all its assignments and mutations, but it does it in a functional, pure way. It's a bit strange, admittedly, since this is an interpreted C instead of a compiled C. Although theoretically, it would be possible for Autology to modify itself so that it reads in C code, compiles it with appropriate system utilities, executes it on the host system, and then returns the value to the running Autology program. I've not done this, but if you think that sounds like a fun weekend project, the repo is very open to pull requests. And finally, there's nothing stopping us from doing this. Since each of these programs returns a number, we can just wrap them together in a single call to plus. And this works. Is it beautiful? Is it heresy? Well, those are both opinions, and Autology doesn't care. This program prints out hello world and then returns 126. So this brings me to the point of the language, or at least as close as I've been able to come to a reason something like this might actually be a good idea. Different languages have different ways of expressing things. Each have their own advantages and disadvantages. Autology asks the question, why not pick and choose which language features make the most sense at every point? Mix and match languages a la carte and always operate in the syntax and semantics that make the most sense and give the most clarity. Well, of course, the reasons not to do this are manifold. The complexity of system, the efficiency of the code, the maintenance of the code base becomes very nightmarish. And anyway, interoperability between languages already exists, right? With a good foreign function interface library, you can write the hot code of your tight loop in C and then call out to that trivially from almost any language these days. So what benefit do we gain from doing this with Autology? And is it worth making syntax highlighting so unreasonably difficult? Because with Autology, we're not actually limited to languages that exist. So, an example, maybe you love for loops in C. That's totally cool, I don't judge, your prerogative. But why not try it with Haskell's range syntax? Well, that's a little bit neater. While we're at it, why don't you use Python's for-in structure? Okay, this is more readable. Why don't we try Rust's Unicode support? Okay, not that one. The point is, we don't have to limit ourselves to using a single language like we would with FFI. We can blend aspects of existing languages together at will and even implement completely novel features at the same time. Now, a common question I get asked is, can't you just do this with macros? And it's understandable. Macros are the normal choice for language extension and syntax modification in Lisp. And yes, many of the things that you can do with this meta-interpretation can be done with macros. However, these two forms of metaprogramming operate with quite different characteristics. Macros are defined in code and expanded at read time, whereas meta-interpretation happens at runtime and could, theoretically, allow modification of the interpreter using data from the file system or from a user prompt. Macros are limited to parsing readable data structures, whereas meta-interpretation can handle anything that you can put in a string. And finally, macros are kept hygienic by using gensims for internally created symbols so that we don't end up leaking and capturing existing scoped variables. Meta-interpretation doesn't care at all and often actually relies on references to symbols which are assumed to be in scope. I mean, we're essentially evaluating arbitrary user-provided data structures, assuming they're functions, and then using those to evaluate arbitrary code. Nothing we're doing here is safe, that's for sure. Okay, so what else could we enrich Autology with? Some other languages have really cool features which would allow your Autology program to be much more expressive, more succinct, or more powerful. We could have the pattern matching of Erlang. We could have the continuation passing style of Scheme. That's nice. Whatever we add needs to be worth a lot because the overhead of modifying the language is pretty huge. What about adding a custom data visualization tool specific to the domain that you're exploring right now? Or a custom debugger keeping track of stack frames, allowing time travel? These are good. What if we abandon all reason and really push the concept to its limits? Well, hypothetically, every program in every language is an Autology program, given some appropriate boilerplate to set up the interpreter. Theoretically, every file on every computer is an Autology program, given some nonsensical and arbitrarily defined interpreter fiddling. What about something less sensible? Let's take a static file containing 1,000 random bytes. First, we can modify an Autology interpreter to treat this file as a valid program, say one that calculates the 20th Fibonacci number. Easy. Then, we can modify a different Autology interpreter to also see this same file as a valid program, but one that does something else, maybe calculate the 20th prime number. Sure. Now, this feels silly, right? We're effectively writing the language to fit the code which already exists. But, I mean, kind of, that's what we do, right? It's certainly what I do when I'm planning a new language. I write snippets that demonstrate the type of expressiveness that I'm after, and then I write the interpreter to fit. But admittedly, in this case, we're probably taking it a bit far, because we're essentially ignoring the actual program. Let's quickly take a step back, zoom out, and look at this interplay between language and program at a more general level. Here we have a diagram depicting some arbitrary computation. You might have to use your imagination. When we want to achieve some computational goal, we use a combination of a language and a program. And it's up to us to decide where the computation actually lives. If we encode the computation directly into the language, we end up with something like the random bytes example, and the program tends towards being completely meaningless. Whereas we could go completely the other way and define almost nothing in the language and do all of the work in the program. In that case, we'd be talking about some kind of machine code or something like the Lambda calculus. In either case, the language defines only the simplest mechanisms by which general computation can be achieved, and all of the rest of the work is left up to the programmer. In effect, we're basically talking about just the differences between high and low-level languages. We've just sort of come at it from a very unusual starting point. Lambda calculus is the lowest level, and the random bytes interpreter is the highest. But what level is Autology? Well, it's a relatively low-level language because it provides the minimum basic mechanisms for computation, or arguably even less than that because, as we noticed, it didn't have functions. But it can transform itself into the very highest level of language. And in this way, meta-interpretation effectively allows you to climb up and down the ladder of language abstraction. You get to choose what balance of language and program is most appropriate for whatever problem you're solving right now, down to the individual S expression. Okay, so just to sum up, Autology is a language that lets you manipulate its interpreter, allowing you to modify its features and character in an incredibly flexible and powerful manner. The project is currently as simple as it can be while still demonstrating the effects of this interpreter modifying metaprogramming. Now, often this sort of language gets referred to as a toy language, but I think that just because we're not building enterprise applications in it, it doesn't mean that it can't be a serious and beneficial tool for exploring programming language design, and more generally, helping us to take a considered approach to how we think about and implement abstractions, from the smallest functions to the largest inter-system APIs. And I'm definitely not just saying that because writing a proper language is a lot of hard work, and I've already done all the easy and fun bits. Anyway, I hope this has been interesting. I've had a huge amount of fun with this project, and it's definitely something I'm going to be playing around with for quite a while. It's been really great to have the opportunity to share what I've been working on, and it's been really exciting to hear what people have to say about it. So if you think that you could help make this project more usable, or if you have a favorite language with an awesome feature that you've always wanted to implement yourself, or if you've just now thought of something probably stupid that you can do with meta-interpretation, then please check out the repo, make a PR, issue, whatever. I'm very open to suggestions. Oh, yeah, sorry. There's the thesis that inspired this project, Professor John Sturdy, University of Bath, 1991. Sorry, last minute, but I didn't want Philip Wadler to be angry at me. Thanks for listening.
Thanks for that. I think you can squeeze it one question. First come, first served.
Thank you. I wanted to ask about some even older work from about 10 years before this. There's a guy called Brian Cantwell Smith who defined a language called 3Lisp, in which you could modify its own interpreter. But the modified interpreter might use some of those modifications. So you had to run code on an entire reflective tower of interpreters.
That's right, yeah. That's, that's also in the thesis that I referenced there. It's the idea of interpreters which are written in languages which are interpreted by interpreters which are written in languages which go up. And you have this dynamically generating infinite stack of interpreters going all the way up. And if you want, even looping back around to the beginning again and being able to reflectively modify all of them in a circle. But I think that would probably make me go crazy trying to implement that myself.
So are you doing that in Autology?
You would probably run out of memory because it's based on Clojure, so you'd have problems. It's not built for that yet.
Thank you. One more round of applause.